So I think what our plan was is we were going to talk about like how the closure stuff works today, with the goal of hopefully getting to. Can you see what's on my screen? Yeah. The goal of eventually figuring out how we're going to do this closure desugaring RFC, right?
Yeah. Right.
Okay. So let me figure out first problem, which of my workspaces we should choose. What's in this one? Okay. Yeah. Let's see. Okay, this is okay. Let me make a little branch here, just because. All right. So, how much do you know about the way Rust models closures, actually?
I just read the rustc guide about the closure part. That that's it. I haven't browsed the code or anything.
Okay. So, like, the first thing is just to understand that when you, let's see, let me show you a few examples here.
I'm not able to see the topmost line when you're writing there.
Yeah, that's weird.
Yeah, now it's fine.
Okay, that's kind of annoying, but I guess we can live with it. So okay, so the first thing is when you make a closure in Rust, this basically corresponds to some struct that implements the FN traits, right? That part. So the interesting thing is if this closure should use a local variable, then we compile this. No, shut up. We basically analyze and figure out. Well, we have two different modes, but in the default mode, we analyze how this local variable is used and figure out what the desugared version should look like, right? So essentially, we're going to make some kind of struct that's like the closure struct. And now we have some choices, right? For this field x that we captured, we could either store a reference. Let's assume x is a U32. We could store a reference to x or a mutable reference to x, or we could just capture it by value. And the way we decide between those three is by looking at how x actually gets used. So like here, even though x is mutable, we're not actually doing anything to mutate x here, we're just reading from it. Then we're going to capture it as a shared borrow. But if we were to mutate x, now we would need a mutable borrow. And we're actually going to get an error here now. And the problem is the problem is that we specified we need an FN closure. But if you kind of desugar this, you're going to have something that looks sort of like this. Something like that. That's what the desugared code would look like. And the problem here is that if you have a shared reference leading to a unique reference, a mutable reference, that mutable reference isn't really unique anymore, right? Because you could copy the shared reference, and then you have two paths that lead to it. So that's the type checker that gets unhappy. So that's kind of the root cause for this error, right? But the way you see it as a user is that we're telling you, hey, you can't use a shared FN closure, you need an FN mute closure, because in order to mutate the state from your caller, you need to have unique access.
So the top one that you have written, FN, foo, the closure, that part, that's not required, right? Like that will be the desugared part. But if somebody happens to write just the main, then and they remove the line x plus equal to the last line, basically where we are incrementing x by 1, then they should be able to compile it just fine, no?
Like this version?
Like what happens if we do not have the oh, I see, okay,
This,
because you are using foo there, but like if you just use the closure, okay, yeah, I get
you
it.
mean like if I just assign the closure to a variable or something?
Right, yeah, that's what
Uh,
yeah.
yeah, this should work just fine. And in fact, it's also okay. Well, with NLL at least. I'm not sure why that didn't error. We're not in NLL now. Well, oh, yeah. So this will work fine. You get if you're in NLL mode,
Right.
you would not. It'll compile just fine because. Oh, shut up. Because the closure's dead here and its borrow has ended. Right? Yeah. The problem is more that we're calling foo. Okay. And so the last thing to show is that there's another option, which is this might be this. You can either, so far we've seen cases where we have a shared borrow, we've seen case with a mutable borrow, but it could also be a move, right? And there's a common misunderstanding about move closures, which I haven't even talked about yet. Like you don't need a move closure to have a move. You can use, like this code is going to, let's just do drop, is going to move x from its parent. So when the closure is constructed, it needs ownership of the vector. So it will go ahead and take ownership, which means if I try to call x here, I'm going to get an error because, like it says, the value is moved into the closure. And so that means I can't use it afterwards. Right? Right. So this is kind of the analysis I wanted to kind of walk through how this works. I think at a high level.
Also, like while we are at this, is there a way to see the desugar version, like the .i file, like in C?
Yes. Okay, that's a good question. I should have showed that to you. One way is you can dump the mirror. This actually generates quite a lot of stuff. If I do dump, well, let's make one that actually compiles. If I do dump mirror equals all, for example, as you can see here, now I'm going to get a directory called mirror dump, and it has a whole bunch of files. Each one corresponds to some version of the mirror for some function as it goes through the transformations. Right. So in this case, we want, let's say, the version of, let's look at the main function. And we might start with like, I don't know. I usually look at the NLL ones actually because they're kind of at a good level of. Oops, my mistake. So if we look at like rustc.main. Blah 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 .nll.mirror, this one here. This contains. Wait a minute. What does this contain? Good question. Let's just clear out this directory for a second. Okay, I don't think I ran with NLL, so you don't get that. But this first file, I think, is the initial mirror that we build, and then we do transformations on it. So this is for the main function. It has a lot of junk.
Right.
The thing that somewhere here, most of that stuff. Okay, so all this code I just skipped over. This is just building the vector.
Right.
It's right around here. This is a little hard to parse, but what's happening is this is the equivalent of saying this. Like we're building a struct, but the name of the struct is this closure.
I see.
And so you can see here that we actually moved the field.
Right.
And if we change this to, if we change our input to, let's say, just here, now we're mutating it, but we're not moving it. And we regenerate these files. Now we can see that we brought in _6, which is an epsilon. So you can really see what's happening here.
Right.
Okay. So let's see. Go back to my notes. Okay, so first of all, you can view the desugared form with -z dump mirror equals all, and open the sort of main dot mirror map. So
not the NLL version, because you initially said that the NLL is more parsable, or you like it better.
well, they're not that different. I just didn't happen to be using NLL in this case, so there was no NLL version. If we did run with NLL, then it would look like basically the same. The main thing is, if you look here, there's all these different versions as we transform the code. They're actually mostly not that different from one another, so you could probably pick any one and it'll be kind of okay. But in some cases, we do like optimizations that might make it like, yeah, okay. So for example, here in this version, we no longer have that _5 equals closure x move. We've sort of rewritten it to just say closure dot x equals, because it's more efficient. So that's why I say like the NLL or this very first one is early enough that we haven't done much, so it looks kind of similar. Yeah. So what happens in the compiler now? So one last thing to mention, I guess, is that all of this happens if you write a default closure. If you write the move keyword, we don't do any of this analysis. We just always move. That's all. But like I said, it's not the only way to move. It's just a way to force you to move. And the way this works is there's like a couple phases. The first thing is somewhere, I don't exactly remember where, I can figure it out. We have this notion of what the free variables of the closure are. I think there's a query or something. Yeah. So what this does is, are you sort of familiar with the rustc query system or not? Or the rustc query system, right? So
I know the philosophy, but which file? So this file lists all the queries, is it?
Yes. This file is I wonder why you can't see the very top. That's so weird. But basically, it's like rustc type query. There's a section in the rustc guide about it. It's probably the best thing. But yeah, it lists all the queries, and then somewhere there's a function that defines this query, which for some reason I'm not finding. Probably because some of the queries are set up in a kind of wacky way. Let's see. Yeah, I don't know. That's something else.
Yeah, I think it's okay. Like you can leave that out in the notes, and I can, or we
Yeah.
can fill it in later.
Yeah. Anyway, somewhere around here, somehow there's a notion of what the free variables are. And this is just the local variables that the query happens to talk about.
Mm-hmm.
So in this, sorry, not query, but the closure happens. So in this case, the free vars would be x. Right? And we say free because they're not bound, like there's no definition of them inside the closure, so they're free.
So can you just say that definition of a free variable again?
So in general, a free variable is a variable that is referenced but not defined by,
Oh, okay.
by something. So you can say the free variables of the closure would be all the local variables that it talks about, but it doesn't define anywhere.
I see.
So in the, if we go into the librusc, oops, where are we here? So if we look at the librusc type check, well, yeah, trying to decide where to start from. I'll start from here. There's this file called upvar.rs, and you can sort of see some of the documentation. It has the job of figuring out, for every free variable, how does it get used? And that determines the mode for that free variable, what we call the borrow kind. Should it be a shared borrow, or mutable borrow, or no borrow at all? Actually, there's another mode I didn't talk about, which is a unique immutable borrow. It's not particularly important, but it's kind of like, basically there's just these levels, that's the main thing, based on how you use it. And that in turn defines sort of the minimum, which traits the closure can implements. Because if all you do is, if you have no free variables or you just read, then you can implement the fn trait, the fn mute trait, and the fn once trait, because you can be called many times in parallel or sequentially, which is like fn mute, or exactly once, it's fine. But if you do more advanced operations, like if you move something, then you only implement fn once, because you can't be called those other ways. You have to be called exactly once. You require ownership, and similarly. So we kind of infer all of this. And the way it works is it uses some kind of old and grotty code, but anyway, that I would someday like to remove, called the expression use visitor.
Okay.
And what this does is it walks the here, like the IO. So at this point, we're representing Rust in this. Are you familiar with the here? It's like the syntax tree.
Yeah.
So it walks the source of the closure, right, in the here, and figures out, it basically calls you back for everything that gets moved, mutated, or borrowed, those kind of things. So it was used to implement the old borrow checker, and it still is. But, so basically it's kind of exactly what we want here. So in this case, it might say, if we go back to our example, if we use x, let's say we use x twice, we say let y equals x of 0. This is going to be a shared borrow of x, because we're reading. And here we have x of 0 plus equals 1. We would get two callbacks. Right? One here saying there's a shared borrow, and one here saying there's a mutable borrow. And it will also tell us what was borrowed. And so those callbacks get invoked on this delegate.
Oh, okay.
By the way, just to, part of the reason I'm videotaping this, because I know it's a lot of information, is I plan to post it on YouTube. So, you know, if some of these notes and things you can probably find later.
Oh yeah, sure, that'd be great.
So the infer borrow kind, so the delegate implements this struct. This struct has a bunch of random stuff, like context information. But the main thing it has is this field that's tracking. So, oh, here it says upvar. That's the same as free variable. That's a term that I don't know why, but rustc uses it. I've never seen it outside of rustc, but for meaning a variable from the surrounding context.
I see.
So somewhere up, I guess. So the upvar closures, this basically is saying for each upvar, what mode did we require? And as we see those callbacks, we'll adjust it, right? So we'll start out saying everything is just read because we haven't seen any uses yet. And then if we see a mutate, we'll bump it up to mutate. If we see a move, we'll bump it up to move. We basically need the strictest one that we actually see. And I think, so the upvar capture map, this is just a hash map going from the ID of the variable, which is some index, to this upvar capture, which tells you it's either moved or it's borrowed. And what kind of borrowed is it? So the actual callbacks, they're here. We get like consume. We get this consume callback if we see a move of something. We get the borrow callback if we see a shared borrow, or a mutable borrow of something. And the rest of them, mutate is when we see an assignment to something. The rest, I guess, don't really matter. So, and in the callback, we get this thing called a CMT, which is an old data structure. It stands for like categorization, mutability, and type, I guess. But basically, it represents, it basically represents what was shared, borrowed, or moved. So in mirror, we call this a place. So like if you had, back to our example, here I have x of 0 plus equals 1. It's actually a bit of there's a little, let's just simplify this for 1 second. If I just had this, now the CMT would just be for a local variable x. We'll see it later. So then we call one of these methods. Basically, based on the kind of thing that happened, we call a method saying adjust the borrow kind for this sort of access. So this would be like for a mutable borrow. This would be for a unique borrow, which I didn't talk about, but that's the point in between. So if a shared borrow lets you make aliases and requires immutability, and a mutable borrow is unique and allows you to make mutation, a unique borrow is unique but still immutable. It's like in between. The compiler uses them internally because there are certain rules of Rust that don't make sense without them. But they're not really something you talk about as users normally. Anyway, that's not so important. But we come into this adjust thing, and here we look at what was the thing that got borrowed, basically. That's what this cmt.cat, that stands for category. It's like, look at the category of this thing. Is it a deref? So that would be like ampersand star x, for example. Or interior means like access to a field. The details aren't, well, you can read them on your own time, I guess. So they're probably not that important, but basically, this basically propagates down. So the idea would be, the simplest case is when the simplest case would be when, what is this? Yeah, I don't know. The simplest case would be like where it's just a local variable, basically. And then the more complex cases are like if you had, let's say we had a tuple here, for example. And we had something like this. Then we would get a CMT telling us that this is x.1, the whole path.
The local variable in the context of the surrounding function, right? Not inside of the closure.
Yes. And actually there's a sort of, that's an important point in some sense that I'm skipping over. no, I should say, because I think that the CMT we get back actually looks a little bit different for those two cases. So you will get callbacks in that call, like for example, we would get a callback here too. And this is a true local variable of the closure. But in this case, in the case where you access an upvar, it's going to look let's see, like this. That's the actual path that you'll get a callback for here. So we sort of see the desugared path. Only there's a little, I forget exactly how this works to look, but because we don't actually know yet, I think, yeah, we see this path always. We always see a star and then the thing. So there's some code. You see here that if it sees a deref of a borrowed pointer, that would be this case, star. Yeah. It's going to go and look and see. So we have this extra notes. It basically says, this note thing is like saying, where did this deref come from? Was this implicitly inserted because it's an access to a closure variable? And if so, then this is where the actual code is that changes. Okay, then in that case, we need to upgrade to a write for x.1, because now we saw a mutation. Or we need to upgrade to a mutable borrow of x, rather. It's this code here. So you will see this distinction that way. So that's basically it, in some sense. When it's all done, once it's walked through the whole closure, you've observed all the things that the closure does, and you've figured out, you have adjusted this map to be, mutables or borrows or shares as it moves, borrows or shares, whatever, as appropriate. Then we just kind of store it. We store it in our. So the output of type check is this whole bunch of tables, which are hash maps, telling different things about the Rust program we just type checked. And in this case, we store and say, here's associated with this closure, here's the set of borrows that we did. Here's the modes for each capture. Yeah. And then we'll also figure out if the closure implements fn mute, or what, and store that information. So that's this part of the code I wanted to walk through a little bit. The question would be now.
So one more thing while we are here, is there a way to like step through the rustc code?
Very good question. Yes and no. So one option is, there are two ways to go about this. You can disable optimizations and build a build with debug info. And then you can use GDB or better yet, RR if you're familiar with those tools. They're sort of similar. I don't know which platform you're on, actually. Are you on Mac or Windows or Linux?
Yeah, I usually use Mac.
Okay. So in that case, I think LLDB is the debugger of choice. And I can point you at some materials on that. And as far as I know, it should work okay. But I don't have a lot of experience with that because disabling optimizations takes a long time. So the problem is that the compiler, you build the compiler, and then the compiler has to build the standard library. So if you turn off optimizations in the compiler, then it runs really slowly and takes a long time for it to build the standard library. You see. So usually we don't turn off optimizations because it's kind of annoying. But if you're willing to wait, it might be worth it. Especially if you're just planning to like walk through and not make changes, then maybe it's worth it. The other thing that I usually do, you see already all these debug statements. My usual strategy is to turn on debugging, just dump everything, save it to a file, and kind of walk through. But that's for what you're trying to do. It's obviously less good because you have to sort of think of the questions before you have them, so that you can print the answers to them. So you could try a debug build. I would be curious to hear how it goes for you.
Sure. Is there a material to see that instructs you how to turn off debugging for rustc itself?
I think there's material about it in the rustc guide, but if not, I'll just tell you quickly that you would open your config.toml
Right.
and change debug equals false to debug equals true.
Okay.
And then I think you probably want to change optimize to false.
Okay.
At least it's been my experience that LLVM is not very good about preserving debug information after doing optimizations. And so the end result is that, like most local variables, it tells you they're optimized out and stuff like that. So you can't actually get a lot of information.
That's helpful. Thanks a lot.
The main thing I would say is if you do this, just build. You want to do a build like with a command like this, where you just build stage 1, so you're not building all the different phases, and you just stop after building the standard library in stage 1, because that's a usable compiler. That'll do the minimum amount of building with your non-optimized compiler that you can get in order to have something that's really usable. You could, in theory, build a little less, but it would be hard. Like you could just build libcore or something, and might be worth it. Just build libcore and write some no standard tests. Like for closures, you don't need the rest, I guess. But I would probably just do this. It'll work most easily.
And if I make changes to config.toml, I don't need to rebuild LLVM, right?
No. But you do have to do a clean build, I think.
Oh, you do have to. Okay, yeah.
You won't.
Yeah,
it shouldn't rebuild LLVM, but
right.
I think otherwise it doesn't take into account the changes that you made. I'm not sure.
Okay. That's helpful. That's very helpful. Thank you.
So I think this information regarding the RFC in question, I think all this information is sort of background that you should know. It's not, well, basically because we're going to have to generalize this system so that we're not storing we're not tracking everything at the level of individual variables, but rather paths. Like that's the goal of the RFC, right? Is that if you do like x.1 and that's the only thing you use, then you should just capture x.1. But
right. Yeah.
I don't actually know. I guess I have to reread the RFC and think about it a little bit. Like I'm not sure, for example, it might be that, right, it might be that there isn't actually a super deep changes. I think that's the hope anyway, that we don't need deep changes to the code here, except that we sort of figure out the set of unique paths that get accessed to a certain extent, and then we track those, and we don't track local variables. But otherwise, the system remains the same. It's just that the resolution of what we're tracking is different. But we can worry about it later. I guess I don't have to think about it as we go.
Right. So the RFC talks about, I forget the actual term, but maybe disjoint variables in the struct, because like if the closure only, let's say there is a struct called foo and the closure only takes into account or like plays with foo.x, then their idea is foo.y should not be ever like considered moved or mutated or whatever. Like it should be able to be used freely. So
Yeah.
is there a portion of the code where the disjoint analysis happens? Like is there, so basically what I was thinking is, let's say if there is a struct and the struct has a variable x, then is there a possibility that I can declare another variable y which takes a reference of x? In this case, x and y, although these are two distinct variables, they are not really disjoint. They are associated with each other.
Yeah, you don't have to worry about that latter case, I don't think, because
Okay.
that'll sort of come up in the borrow checker that if you've borrowed a field. So I think from your point of view at this stage in the code, we can think of all the local variables as disjoint. And then the borrow checker's job is to ensure that this is true, like as much as it needs to be true. So it's probably okay if they overlap as long as it's only shared borrows, for example. But um, I think the challenge here is going to be that there's a bit of a gap between like the mirror operates on desugared stuff, and here in the type check phase, we're still sort of in a semi-sugared world. And some of these paths can get kind of complex, like with deref and overloaded deref and other things. And I'm not sure. We have to sort of. We'll have to work through that. I imagine we can start with very simple cases where we don't have where those things don't apply. So probably where we will start. I would imagine a good first PR might be to try to write an analysis that just basically to generalize the free variables. So we might, yeah, that makes sense. Like the first refactoring probably is to change so that we're not representing free variables always as just local variables, but rather as something that can be more, that can accommodate more complex paths. I'm not sure exactly what that is yet, but like the very first refactoring is probably just introduce a new struct so that we can make changes to this struct later, if you see what I mean. So like these maps, like the, where was that map we were looking at? Well, this with free vars, for example, this tells you all the free variables in the closure, and then we have this upvar ID that everything is keyed by, right? So like, there's an example. So this map stores the mode, shared, mutable, or move, and it's keyed by upvar ID. So that'll probably have to change to like upvar path or something, if you see what I mean, so that we can even talk about the idea of capturing something that's not a local variable. And then, because right now we just can't even represent it. That's sort of, we could start, I don't have it at the top of my head, but I think the series of PRs will be something like, first we have to introduce a new type here, and we'll just push that through, but that new type will just be a struct that wraps the upvar ID, so like none of the code really changes, but there's still a lot of like grunt work to push it through. And then once that's in place, then we can like start adding some new cases, more complex cases, and we won't use them at first, but we can sort of decide what's the right order to do it in. Like maybe we'll generate. Well, okay. What I imagine is that we'll add some more complex cases. It'll be feature gated, and we'll start with the easy stuff. Like if you have a tuple and you use .0 and .1, that's like relatively few complications. Get that to work, and then we'll gradually expand. So the next piece of code will probably be something after we do that grunt work that looks at the paths that the closure uses and decides what the upvar paths that it captures ought to be. And when we first write that code, it'll always yield just the set of upvar IDs, so always simple paths, and then we'll go. Yeah. Anyway, I think we'll worry about that path later, but that's the basic plan I have.
And, can you show me the place where the concept of paths is used? Like path is basically from module to a variable, is it? Like
this kind of path, I mean, is more like a.b.c, like a series of field accesses. there isn't a very clean representation of a path, but that's one of the challenges we have to figure out how to overcome. But I think the closest thing is this CMTs,
I see.
which they have a path, basically. So if you look at them, they have a category. The category is like deref, so that would be like star P, where P is also a path. And then they recursively have a structure. Right? So A.B.C would be a series of interiors until you get to the local variable or the upvar, which would be A or B. So that's kind of what it looks like. And this data structure isn't really suitable for what I'm talking about, I don't think. I don't think we have a good data structure for what I'm talking about. So we probably have to make, like, in other words, this upvar path data structure that I was referring to doesn't really exist. We have a way to talk about, we have here expressions. I don't know, we have a couple of things. I don't think any of them are quite right. So I'll have to think about that. But
yeah, we can create a data structure if it doesn't exist for our purposes.
Right. The CMT might be okay. Maybe we'll use that. But I sort of like that to. I always sort of like that to go away. It's very old code and it's very grody. You can sort of tell that it's old because like it doesn't follow our naming conventions, for example, right? It starts with a lowercase letter, whereas in modern Rust, structs start with an uppercase letter. This predates that convention, among other things. But so yeah, I sort of rather make a clean new thing, and we'll get rid of this old thing. But,
yeah, I think while we are at it, we can also clean up some of the code.
Right.
As we go. Right. Yeah, that makes sense.
So do you think? Do you feel like you can try to write down some of what I said? Does that seem too ambitious?
No. I think it will be a good learning for me to like what you said. I'll probably stick a debugger, go through it, and then also compose my notes for rustc guide. And I think
yeah, that would be awesome.
Yeah, to help me get a better understanding, and then someone who is reading it who probably will have less work to do.
Yep.
So yeah, totally. Will it be possible to get a link to this video later on?
Yeah, I'm gonna. As soon as we get off, I'll start encoding it. That usually takes a while, and then I'll post it up, and I'll send a link.
Yeah.
It'll be on my like. I'll send it to you, but I have also a playlist of like videos like this, so I'll put it in there.
Oh, okay. Yeah. Do you? Okay. Yeah. So if you can send me the link to that playlist.
Yep. I need to advertise it better probably, but I don't know that it has anything else that you might want, but it can't hurt. I'll send you the link.
Oh, okay.
All right.
Thanks a lot.
Cool. All right. I gotta run. I'm hungry. It's lunchtime.
Oh yeah, it's lunchtime for you. Thanks a lot for this call. It was actually really helpful.
Good. Great. I look forward to it.
All right.
See you later.
All right. Talk to you later.